Though referenced in H.G. Wells' The Time Machine, the actual science of time travel didn't come into being until well into the 20th century as a side effect of Einstein's theory of general relativity. It was developed in 1915. Relativity describes the physical fabric of the universe in terms of 4 dimensions. This is called space-time, which includes the 3 spatial dimensions, up, down, left, right, and front, back, along with 1 time dimension. Under this theory, which has been proven by numerous experiments over the last century, gravity is a result of the bending of this space-time in response to the presence of matter. In other words, given a certain configuration of matter, the actual space-time fabric of the universe can be altered in significant ways. One of the most amazing consequences of relativity is that movement can result in a difference in the way time passes, a process known as time dilation. This is most dramatically manifested in the classic twin paradox. In this method of time travel, you can move into the future faster than normal, but there's not really any way back. In 1937, Scottish physicist W.J. van Stockholm first applied general relativity in a way that opened the door for time travel. By applying the equation of general relativity to a situation with an infinitely long, extremely dense rotating cylinder, kind of like an endless barbershop pole. The rotation of such a massive object actually creates a phenomenon known as frame dragging, which is that it actually drags space-time along with it. Van Stockholm found that in this situation you could create a path in 4-dimensional space-time which began and ended at the same point, something called a closed time-like curve, which is a physical result that allows time travel. You can set off in a spaceship and travel a path which brings you back to the exact same moment you started out at. Though an intriguing result, this was a fairly contrived situation, so there wasn't really much concern about it taking place. A new interpretation was about to come along, however. In 1949, the mathematician Gert Gödel, a friend of Einstein's and a colleague at Princeton University's Institute of Advanced Study, decided to tackle a situation where the whole universe is rotating. In Gödel's situation, time travel was actually allowed by the equations. If the universe was rotating, a rotating universe could itself function as a time machine. Now, if the universe were rotating, there would be ways to detect it. Light beams would bend, for example, if the whole universe was rotating. And so far, the evidence is overwhelmingly strong that there is no sort of universal rotation. So again, time travel is ruled out by this particular set of results. But the fact is that things in the universe do rotate, and that again opens up the possibility. In 1963, New Zealand mathematician Roy Kerr used the field equations to analyze a rotating black hole, called a Kerr black hole, and found that the results allowed a path through a wormhole in the black hole, missing the singularity at the center and making it out the other end. This scenario also allows for closed time-like curves, as theoretical physicist Kip Thorne realized years later. In the early 80s, while Carl Sagan worked on his 1985 novel Contact, he approached Kip Thorne with a question about the physics of time travel, which inspired Thorne to examine the concept of using a black hole as a means of time travel. Together with the physicist Sung-Won Kim, Thorne realized that you could, in theory, have a black hole with the wormhole connecting it to another point in space held open by some form of negative energy. But just because you have a wormhole doesn't mean that you have a time machine. Now let's assume that you can move one end of the wormhole, the movable end. You place the movable end on a spaceship, shooting it off into space at nearly the speed of light. Time dilation kicks in, and the time experienced by the movable end is much less than the experienced time of the fixed end. Let's assume that you move the movable end 5,000 years into the future of the Earth, but the movable end only ages 5 years. So you leave in 2010 AD, say, and arrive in 710 AD. However, if you travel through the movable end, you will actually pop out the fixed end in 2015, since 5 years have passed back on Earth. Well, the fact is that the two ends of the wormhole are connected. No matter how far apart they are in space-time, they are still basically near each other. Since the movable end is only 5 years older than when it left, going through it will send you back to the related point on the fixed wormhole. And if someone from 2015 AD Earth steps through the fixed wormhole, they'll come out in 710 AD from the movable wormhole. If someone stepped through the wormhole in 2012, they'll end up on the spaceship somewhere in the middle of the trip, and so on. Though this is the most physically reasonable description of a time machine, there are still problems. No one knows if wormholes or negative energy exist, nor have to put them together in this way if they do exist. But in theory, it is possible.